welcome everyone. It's a very great pleasure to have Antony Lewis here today. Thanks a lot for accepting our invitation. Antony is Professor of Cosmology in the Schools of Mathematical and Physical Sciences at the University of Sussex. He obtained his MCSc in Physics from the University of Cambridge and then completed his PhD at the Cavendish Laboratory, working on geometric algebra and covariant methods in physics and cosmology. He began his postdoctoral career at DAMT in Cambridge before moving to the Canadian Institute for Theoretical Astrophysics in Toronto, with a period at the Centre for Astrophysics at Harvard. He later returned to Cambridge to join the Institute of Astronomy on an STFC Advanced Fellowship, and after that he moved to Sussex, where he has been ever since. Antony's work has been foundational in modern cosmology, from the physics of the early universe to cosmic microwave background analysis, parameter estimation, development of numerical tools that have become standard across our field. Today we will present what the acoustic scale observations tell us about dark energy. Antony, please, you can start when you're ready.
Great, thanks very much. I was going to try to talk a bit about what CMB and BAO observations tell us about the dark energy, in particular, sort of putting physical constraints and how that translates into the directions in which observations can move, and hence what particular types of observations tell you. So I'll start with a bit of an introduction about the acoustic scale. So if you're familiar with that, you might want to doze off for 5 minutes, and then I'll go a bit more through the detail of what exactly I'm going to be talking about and deriving some inequalities and pictures and discuss how it relates to the standard parameterizations of dark energy. Right, so just to remind you, the standard picture, we're starting with a hot big bang. So the early universe is ionized in a plasma. And I'm going to assume for the purpose of this talk, we basically know the physics that's going on in this hot big bang era. So the universe contains stuff that we know, the physics is stuff that we know, so we can model it. So I'm not going to be talking about early dark energy in this talk. I'm just talking about the late part. So I'm going to assume the bit before recombination is all quite well understood and the standard physics. And then recombination, of course, is when the universe becomes transparent. So what we see in the microwave background is this recombination surface at redshift for 1,000 or so. And we can also observe galaxies and the clustering of galaxies at late times. And we can hope to measure the acoustic scale, both at the recombination surface and in the galaxies at lower redshift. If anyone hasn't tried it yet, this is generated with the latest image generator, which I thought was quite impressive, really, on the second iteration. Okay, so what do we think happens for the CMB, first of all? I'll talk about the acoustic scale and the CMB, where that comes from, what exactly we measure, and what can be robustly measured independently of the dark energy. So we think the hot Big Bang started with the scale invariant spectrum. So the left picture here shows the sort of scale invariant spectrum where you've got blobs of all different scales, large and small, of equal amplitude. And then the universe evolves in this hot, dense plasma, and structures grow on larger and larger scales as the pressure waves in the fluid have had time to travel further. So you get larger and larger structures forming as you have more time for things to collapse. And then at some point, the universe becomes transparent at the recombination epoch, and that's what we see. We see a snapshot of redshift for 1,000 when the universe looks something like this. And there's now a characteristic scale on this last scattering surface that we see, given by the largest perturbation that's had time to collapse at recombination. And because I'm saying we think we know what the physics is in this early universe, this is something we can model, so we know, given the initial conditions, where it should end up after a given time, modeling the atomic physics of when recombination happens. And then the characteristic scale you see here, there are now lots of hot and cold spots of this sort of characteristic size, and RS is the sound horizon scale. So this is what I mean by the acoustic scale. It's the size of the largest perturbation that's had time to collapse around the time of recombination. So it's a very characteristic size that we see in the observed microwave background. So then we observe the microwave background all around us on the sky today, and we can measure it light coming from redshift for 1,000. After recombination, the universe is more or less transparent, except for after reionization when there are some free electrons again. But of course, the universe expanded by a huge factor between redshift for 1,000 and redshift of 7 or something. So the electrons are very sparse in this late part of the universe. So the impact of them is relatively small. You only actually lose a very small, fairly small percentage of the photons. You more or less see a direct image of the whole last scattering surface about us in the microwave background. So we've got this spherical shell over which we can measure the sound horizon, and the distance in the standard ΛCDM model is about 14,000 megaparsecs co-moving away from us. Okay, so what we see, I'm showing here us on the left, the hot Big Bang, start of the hot Big Bang on the far right, and recombination, which is when the universe becomes transparent, which is the surface we see in the microwave background. And then your sound wave travels outwards from the hot Big Bang towards recombination and reaches some maximal size at the time of recombination. And then what we can actually observe is not the sound horizon itself, but theta star, the angle that this characteristic size subtends on the sky today. So what we really measure is theta star here, the angle on the sky. And this is measured now incredibly well because we've measured with Planck and other observations over the full sky, these perturbations. We've measured lots and lots of these sound horizon scales. So this scale is now measured at about 0.03% precision. So it's known about as well, almost as well as the microwave background temperature itself. So in the same way that people often don't talk about the background temperature of the CMB as being a parameter, you could also more or less regard this as being a fixed parameter at the same level of precision within a few technical caveats. And the angular diameter distance to the last scattering surface here, you will know if you know what the sound horizon scale is here. So I'll now try to explain how we know what the sound horizon scale is in the co-moving physical scale at recombination. So this is the scale that we actually observe, RS the sound horizon. We measured the acoustic peaks measured in L in angular scale, and this sound horizon scale in the acoustic power spectrum just corresponds to the position of this first peak here. And because there are so many peaks also in polarization, it's very well measured. So we're regarding it as a fixed constant. So how we know the parameters of this early universe is from this detailed picture of the shape of the microwave background spectrum in temperature and polarization. So I'm going to assume now that T naught, the CMB temperature, and theta star are both known very well. And for the moment, let's just assume the matter density is known very well as well. And then if you look at what happens when you vary the baryon density, then you'll see that there's a very characteristic prediction for the up and down, raising and lowering of the acoustic peaks as you vary the baryon density as shown by the color here. So the baryon density affects what you expect to see on the recombination surface in a very predictable way. And then by looking at these detailed measurements of the shape of the power spectrum, you can measure the baryon density at recombination. And that allows us to measure that to about 1% as well. So it's not measured as well as the temperature and theta star, but it's still at the percent level, so it's quite well known. And now if we say, well, now with the baryon density is known, and we know theta naught and we know theta star, you can then look at what happens when you vary the matter density. And when you vary the matter density, which is the baryons and the cold dark matter, I'm assuming, which I'm again assuming is a standard physics, that varies in a very predictable way that's quite different to the way that the baryons affect things. So it just moves the whole spectrum up or down with some scale dependent that you can predict quite reliably. And again, this is imprinted, this change in the shape is imprinted at recombination. And you've got a measurement of it, which is at the percent level as well. So this is also well measured, the matter density, from the shapes of the power spectrum in the microwave background. So this is going back to this picture here with this sound horizon scale. But now we can try to predict what this sound horizon scale should be because we know the contents of the universe. We know there's baryons, dark matter, photons. We know because of the start of the hot Big Bang, everything was in thermal equilibrium, so we can predict the number of neutrinos that there should be. We know the CMB temperature, so that allows us to predict the density of neutrinos and the density of the photons. And then these peak positions tell us the matter density and omega b h squared. And once you've got those, that's actually enough to solve for the background expansion of the universe, work out when recombination happens, and then integrate the sound speed into co-moving distance between the time of the hot Big Bang and the time of the recombination surface. And if you do that, you end up with this prediction for the sound horizon scale about 144 megaparsecs. Again, known to really quite good accuracy, assuming we know the physics of recombination. So now, if we know that sound horizon scale and we've measured theta star, that allows us to infer the angular diameter distance to the last scattering surface, dm. So this is the co-moving angular diameter distance I'm going to call dm, which is about 13 gigaparsecs with a reasonably small error bar. And if you assume flat lambda CDM cosmology, you can then translate that into value of the Hubble parameter, which comes out as about 67, as is well known and a bit discrepant with the more direct measurements we have. But of course, if it's not lambda CDM, then this number can vary quite radically, depending on the evolution between recombination and today. So for the purpose of constraining dark energy, it's quite useful to try and focus on things that are actually independent of the late time evolution and independent of what the dark energy model might be doing. And you can really do that quite well because what you're seeing in the microwave background is mostly coming from recombination. And the main effects that change it after recombination are CMB lensing, and so that's distortion by matter along the line of sight. And on large scale, something from the integrated Sachs-Wolf effect and rescattering at reionization. So lensing potentially does actually affect all the scales in the spectrum. But the nice thing about it is that it gives you a non-Gaussian signature. And you can measure that non-Gaussian signature in the 4-point spectrum empirically. So basically, by measuring the 4-point function of the CMB, you can constrain empirically how much lensing there should be as a function of scale. And from that empirical measurement of the amount of lensing, you can work out how much the primordial spectrum should have been processed by the lensing. And you can do that in a way that's independent of cosmology. It just requires an empirical measurement of the 4-point function. For the ISW and reionization, that's maybe a bit more tricky, but these only affect the very large scales. So you can, for example, put a cut in and remove the very lowest multipoles to remove the effect of the ISW. Reionization affects the polarization on large scales, but on small scales, all it does is move the whole spectrum up and down by a predictable amount set by the optical depth. So you can just factor out that overall scaling in the amplitude, and after that, the amplitude is well determined by recombination and a combination with the optical depth. So what this means is that by using the lensing data in the 4-point function, you could then marginalize out the remaining uncertainties in the shape of the lensing spectrum independent of cosmology, cut out the other stuff, and what you're left with is something that depends basically only on the physics of recombination. And since I'm assuming we know the physics prior to recombination, you can then constrain these parameters. So here I've shown constraints on these 5 parameters on the left here. So early lambda CDM means only assuming lambda CDM until recombination, but marginalizing out these lensing and cutting out the other effects, compared to assuming lambda CDM at the whole time all the way down to redshift 0. So of course you lose some information by doing this because it's a more open model. This works for absolutely any dark energy model here. But you can see also that the increase in the error bars is pretty modest. So actually most of the parameters measured by Planck are actually measured in a way that's more or less independent of dark energy, assuming we know what's happening in the early universe. So this is some useful constraint to use if we're trying to combine with late time observations to constrain dark energy. And in fact, the DESI team used precisely this to use their Planck data in a way that was independent of the late time cosmology. Okay, so that was the microwave background. What about the baryon acoustic oscillations? So the microwave background is a recombination in the photons. The acoustic oscillations are imprinted from the baryons, which is a slightly different scale because the baryons decouple later than the photons decouple from the baryons. But it's very similar, and it's predicted at similar precision. So we know basically what this drag scale is for the baryons, which is also the same, which is basically the same acoustic scale, and they scale in exactly the same way. And then what you actually measure is the correlation function as a function of redshift and angle on the sky. So if you think about the correlation function in the transverse direction, in the theta direction, then what you're measuring is this theta BAO parameter here. So you're measuring the same co-moving distance that was imprinted at recombination in the transverse direction, and what you're measuring is an angle on the sky of that correlation. So that depends on RD over DM. And you can also measure the change in redshift between the start and end of this characteristic acoustic scale along the line of sight. And that translates into this change in redshift translates into a measurement of the Hubble parameter at that redshift. So by acoustic scale observations, I mean using the microwave background, a particular theta star, and the other information for recombination, and combining that with the BAO, which gives you extra information at low redshift. So these BAO observables, I'm going to call DH the Hubble distance, which is just 1 over the Hubble parameter for the line of sight distance, and the transverse distance is the co-moving angular diameter distance to that redshift. And if you write out how the angular diameter distance is related to the Hubble parameter, then it is just the integral of 1 over h over dz. So in fact, dm, the angular diameter distance, is just an integral of dh. So these two observables are related in the theory by an integral sign. Alternatively, you can also make another parameterization, dV and FAP. So dV is like a volume averaged measurement of the scale, and FAP is the ratio of the horizontal and the transverse, sorry, line of sight and transverse distances. So DM and DH are things you can measure. Alternatively, you can measure DV and FAP. They just contain basically the same information. They'll have slightly different degeneracies, but there's alternative ways of encapsulating the same information. Okay, so we've got this BAO data and we've got the CMB data. So how can you vary the dark energy model and be consistent with this data that we have in ways that we think might be physical? So I'm going to assume theta star is fixed and the early universe parameters are fixed because we know what's happening at recombination and the microwave background has measured them very well. So we know matter density, we know the baryon density. So we know all these acoustic scales, we know RS and RD. And because we know the matter density, that tells us rho m, and we're assuming the matter is cold dark matter, so it evolves as a function of time. So the only thing we're varying is the late time dark energy model. And then because theta star is basically fixed, and we know the sound horizon, that would tell you that dm is fixed. And this argument I'm going to make, although these parameters aren't fixed, you can also make at any given point in parameter space, if you're considering sampling over parameters, for example. So the other constraint I'm going to use is the null energy condition. And what I mean by the null energy condition is that it's non-phantom in the dark energy. So I'm going to assume the dark energy is a separate component of something that doesn't interact with the matter or the baryons or anything else. It's a non-interacting component. And on its own, it obeys a null energy condition. In terms of cosmology, what this means in a homogeneous universe is basically the density of the dark energy cannot increase with time. So as you expand a box, the energy density inside that box cannot increase. And in terms of redshift, that means that the energy density of the dark energy has to increase with redshift. So I'm going to see how this constraint translates into constraints in the way in which the BAO observables can change. So DM, which is now fixed, remember, because we've got the theta star is fixed. I'm going to say it can either be the value in some dark energy model, a general model, or we can fit lambda CDM to it. But at the end of the day, if it's going to be a fit to the data, the value of DM has to be the same because we have to fit the same data. So whatever dark energy model we choose has to give you the same integral of DH as it does in the lambda CDM model. And if you write down what this DM, your angular diameter distance, is in terms of redshift, so an integral of dz over h, and then translate h via the Friedmann equation into the densities, you can write this equation as these two integrals here, relating an integral of the matter density and the dark energy density for the dark energy model versus the matter density and lambda, assuming a cosmological constant. And they have to be the same because we have to predict the same acoustic scale in the microwave background. That has to be, which is now measured very well, so you can't vary that. So then if the dark energy density is increasing with redshift, and these two integrals have to be the same, so this thing is only monotonically changing, that means you have to start the dark energy at low redshift as being less than the value in lambda CDM. So that means that if you translate that by the Hubble equation into the Hubble parameter, that tells you that the Hubble parameter inferred in a dark energy model has to be less than the value inferred in a lambda CDM model. So in particular, if you include null energy consistent dark energy model, that means you're only going to get your inferred value of H naught being lower than it would be in lambda CDM. So if you're trying to fit local measurements for the Hubble parameter that give you higher values, you can't do it by models that are consistent with this non-phantom neck condition where the energy densities are only increasing with redshift. So if you look what happens to the evolution of these BAO parameters as a function of redshift, it looks something like this. So here I plotted on the left DH, the Hubble distance, versus subtracted to the value in lambda CDM. So at low redshift, the Hubble parameter is lower than lambda CDM, so DH is higher. And this, what I've plotted here is just some typical Thoring model. So this would be something like a scalar field model, which is Thoring and hence obeys the null energy condition because it has a sensible Lagrangian. So it starts up here, but we know that the integral has to give you the same as in lambda CDM. So that means that the average, the integral over this whole range of redshifts has to go to 0, which means that at some point it has to cross 0. So at some point ZC, a critical redshift, at which the value of the Hubble parameter is in fact exactly the same as it would be in lambda CDM, and hence DH is the same as it would be in lambda CDM. And once you go to very high redshift, because we know the DM has to be the same, and I mean, assuming that the early universe is the same, so it's matter dominated, then DH has to go to the same value at high redshift. So this ratio has to go to 1 at very high redshifts. So you can then think about what this actually means. Well, at Z less than the critical redshift here, DH is always bigger than the lambda CDM model. And that means if you write down the angular diameter distance, which is the integral of DH, that has to be bigger than the value you would get in lambda CDM. So the angular diameter distance at Z less than ZC has to be bigger than the value in lambda CDM. If you're higher redshift than this critical redshift, then you can write down the rate of change with redshift of this distance of the difference in the angular diameter distances. And because dm and dh are related by an integral, that is just dh minus dh lambda. And above ZC, by definition, that is negative. So what that means is that these two things are approaching each other in a monotonic way, and that because they're reaching at high redshift the value of 1, that means that you can never actually go below the value that you had at ZC. So in fact, the angular diameter distance in any dark energy model that satisfies the null energy condition has to be bigger than the value in lambda CDM at all redshifts. And you can play this game with all the other BAO observables as well. So you can derive a set of inequalities, which I've shown on here. So I'm not going to go through all of these in detail. I've talked about some of them. So this is the constraint about the Hubble parameter having to be less than in lambda CDM. This one just comes directly from the Friedmann equation and the null energy condition. dm has to be always bigger than the value in lambda CDM. It varies monotonically and decreases to 1 at high redshift. The Alcott-Pociński parameter has a similar inequality where the value in any dark energy model that satisfies null energy has to be larger than the value predicted in lambda CDM. For dV, the angular averaged one, it's not quite so clear, but it has to be larger at low redshift, and at high redshift, it obeys this slightly more complicated, this slightly more complicated inequality, which actually allows it to go a little bit the other way. So it doesn't have to be strictly bigger than the value in lambda CDM at all redshifts, but in practice, it always turns out as being bigger at low redshift and only very slightly below at high redshift. So what this means is if you've got some BA observations, you can tell more or less directly from what the BA observations are, whether they're going to be consistent with a null energy consistent model of dark energy or not. So what I'm going to do is I'm going to plot either dm against dh as on the right here. So I plotted the ratio of dm to the value in lambda CDM and dh the value in lambda CDM. So the central point here is just lambda CDM at all redshifts. And on the left, you can also alternatively do it in terms of the Alcott-Pociński parameter FAP and dV. And because of these inequalities, there are regions of this parameter space shown in gray that are not consistent with deviations that are consistent with a null energy condition about the lambda CDM model. And if you start with something like a Thoring model, then the color in this line here shows the evolution with redshift of the Thoring model. And of course, that obeys the null energy condition, so it stays entirely in this allowed quadrant of the plane up here as it evolves in time. Alternatively, if you look at something like the best fit to the DESI model in the W0 WA model, then you will find that actually it can lie almost entirely in this excluded region. So all these points down here are directions that you can't go without validating the null energy condition. And you can either draw this in the left-hand plot or the right-hand plot. You get more or less the same qualitative picture. It just looks slightly different depending on whether you rotated the parameters or not. So DESI results are the thing that sparked a lot of interest in this. So we've now got DESI data release 2, and these are the plots from their paper showing their results. So they don't actually plot these two parameters against each other, so you can't see the correlations and things easily in these figures. And in fact, they're plotting Planck as the dashed line in here. So you can see that their data points are all lying what looks like systematically below the best fit lambda CDM model. If you vary the lambda CDM model just with the BAO data, then of course you can fit it quite well because you're not constraining it. But of course, adding CMB, which is what I'm interested in doing, then things get significantly more constrained. So this generated quite a lot of interest because there looks like there's some sort of discrepancy going on here. And then the question is, what kind of models could be consistent with this kind of deviation in the data, or is in fact it just a fluctuation? Could it be something just you'd expect to see in lambda CDM or not? So I'm going to replot this DESI data in these two parameters. So I've colored the points here by the redshift of the data that's being considered for the different redshift bins in the Baryon acoustic oscillation data from DESI. And you can see the points on here compared to the central point, which is the Planck best fit lambda CDM model. And the data points scatter around, and maybe this point down here in particular looks a little bit discrepant, and this one is also a little bit discrepant. So that's where the sort of tensions are coming from. But you can see that this one, the LRG2 point, is clearly in the region in which you can't vary the theoretical model and be consistent with the null energy condition. So if anything, this is all these data points, if they're not consistent with lambda CDM, look as though they're pulling you into the region that's not actually allowed by the null energy condition. So I'll talk later about possible other interpretations of that. So what people often do is actually fit to this CPL model, this W0WA model. And if you take that seriously and just work out the predictions for the BAO observables at different redshifts, and do a sort of sampling run to get all the samples of the allowed parts of the parameter space in that model, and then work out what the DM over DH and DM over DM lambda, DH over DH lambda look like at each point in parameter space and plot those, then you get the contours shown on the left here. So what this shows is that for basically almost all of the points in the parameter chains, when you fit the W0WA model, the predictions at each point in parameter space for the two distances are in a direction that's inconsistent with consistency with the null energy condition and the Planck model. If you combine that with Pantheon plus Supernovae data, it shrink the contours a bit, but you can still see that almost all of the volume of the posteriors here is lying in the excluded region, or maybe you're just about on the corner and still consistent with lambda CDM in the middle there. So of course, nobody really takes this W0WA model seriously. People normally argue that it's a convenient parameterization that allows you to make predictions for observables that you can then test the lambda CDM model with. And so the question then is, if you have W0WA, you make some parameter constraint, how does that actually map into the regions that are allowed by the null energy condition or not? So if you fix the matter density and you fix theta star from the CMB, then each point in this plane basically corresponds to a value of H0. So the black line at the bottom here is the line that corresponds to the value of the Hubble parameter being exactly the same as it would be in lambda CDM. And then the colored lines are showing you what the predictions are for the value of these BAO observables. So I've chosen to plot DM here. So green one, for example, is the line where the prediction in the dark energy model for the BAO observable is exactly the same at redshift of a half as it would be in lambda CDM. So the way to think about this is that if you're lying above this point here, then you are consistent with the inequalities for the direction in which DM can vary. But if you're below this line here, then you're inconsistent with the inequalities for the way that things can vary in null energy consistent dark energy models. And on this line, the predictions of lambda CDM for redshift of 0.5 will exactly agree with the values in lambda CDM. So that's, of course, why the BAO posterior constraints lie along this kind of direction, because more or less the data fits lambda CDM at 0th order, and therefore it lies along this sort of direction where the predictions to lambda CDM are very much similar. So these colored lines here are just different redshifts. So this black line is actually the limiting case where, in fact, the predictions are not consistent with the null energy condition at any redshift. The top line is where things become consistent with it at all redshifts. And then these other lines in the middle here tell you about different redshifts of the observables that you're looking at. So by considering these lines, you can think about where the contours are, and then hence whether your constraints and your predictions for the observables are actually in the direction that you would expect or not. And if you plot the DESI posterior constraints, you get something that looks like this. This is various combinations with microwave background and DESI, or including supernovae as well. And the dashed lines here are some of the lines from the previous figure. So this line here is the constant H0 equal to that in ΛCDM. This is one where everything is consistent with the null energy condition. And this line here is where dm at redshift 0.5 is consistent with the null energy condition. So the BAO data are constraining around 0.5 as one of the best constrained redshifts. And you can see that actually most of the parameter volume that's being constrained here is actually below that line. So if almost all the parameters points in this parameter space, the predictions of the W0 WA model are in a direction that's inconsistent with the null energy condition for the redshift of the observables that are actually being measured. So these constraints are very dependent on the fact that this model allows you to have things that are null energy violating, in other words. So you can, for example, impose a prior that W0 has to be bigger than -1. And if you do that, you end up with contours that look completely different, as I've shown on the right here. So these contours on the left strongly depend on allowing null energy violation. So that seems a bit weird. So you might think, well, how about lambda CDM? Lambda CDM doesn't actually look too bad, or does it? So on the left here, I've shown a plot from the DESI paper showing the constraints from the CMB alone and the DESI constraints combined with BBN and theta star for omega m versus H0. So you can see here that the CMB constraint does look as though it's off on one side in the lambda CDM model compared to the DESI. On the other hand, the direction of this degeneracy is pointing exactly towards where the DESI data is over here. And if you imagine the truth lies somewhere like, say, here, then you're actually consistent with both data to within one or two sigma. So one plausible explanation perhaps for the DESI data is that Planck data fluctuated a bit in this direction up here, and the truth lies somewhere here. And if we're prepared to allow that fluctuation, then maybe things aren't too bad. And I think there's some sort of indirect evidence that that's kind of the direction we'd have expected Planck to fluctuate in if it fluctuated. And of course, you don't expect things to land at exactly the mean of the error bars. You expect fluctuations of 1 or 2 sigma along this direction. So we shouldn't be at all surprised if there is a fluctuation. You get a similar kind of picture if you do it with ACT, as shown in this slightly later picture down here. Anyway, if you take this point seriously and sort of say that this is actually the truth here, this is the lambda CDM model. So we're going to shift the value of H0 up a bit and omega m down a bit for the CMB. And now I plot the BAO data compared to that best fit model in the center here. And I plot the DESI data. This is what they look like. And to me, by eye, this looks like a pretty decent fit of some data points at a bunch of redshifts to the central point with some scatter from the expected scatter of the data. And if you look at what happens with DESI1 versus DR2, so here, again, the central point is the best fit to Planck plus DR2 best fit lambda CDM model. So if that was the truth, what you would expect is the data points, as you get more data, to cluster in on that value. And you can see that the error bars are shrinking, and the central points are indeed moving towards the central value. So they could have done some other things like moving apart, but they didn't. They actually moved towards the center. So of course the error bars are shrinking as well, so it doesn't necessarily get more consistent. But it doesn't look to me by eye to be a bad story that lambda CDM could just be true. Got a bit of a fluctuation, but it's not a bad fluctuation. And omega m is a little bit lower than we thought from Planck initially, just due to some statistical fluctuation in that measurement. So what then becomes interesting is if you talk about the supernovae as well. So I've only been talking about acoustic scale observations so far, but the supernovae are actually partly what is driving, or mainly, in fact. They were the first people to suggest some evidence for some funny dark energy model. And if you look at what's happening with the supernovae, basically everything is coming from this sort of low redshift region down here, where this point is high compared to the black line. The 3 different panels here are 3 different supernovae compilations. So you can see that things are shifting around a bit depending on exactly which compilation of data you look at. But this pull this point being high here is basically pulling parameters when you combine things with supernovae, using this data into a region which favors these funny dark energy models that are null energy violating more strongly. There was more recently this DES-Dovkey reanalysis of the DESI 5 data where they recalibrated and some other things of these low redshift supernovae, and they do actually find a shift that goes a little bit in the direction of lambda CDM. So in that paper, they're only concluding there's only weak preference for evolving dark energy. And even if there was dark energy and using supernovae, and you're using that as the evidence, it's a pretty strange argument to make that we're going to introduce this really weird null energy violating fluid with these extra parameters. And then you go and calculate H naught, and you find that H naught comes out to be very similar to the value predicted in lambda CDM. In other words, it's far too low to match the value actually measured by the calibrated supernovae. So including these W naught WA models does not solve the Hubble tension for you. And it seems rather bizarre to think that that might be a good solution to anything if you haven't actually solved the Hubble tension still. But what else could be going on if there's something interesting? So I've just been assuming so far that the extra dark energy fluid was a separate non-interacting fluid that's just some dark energy that's there. But there are other possibilities. I mean, you could have interactions between the dark matter and the dark energy. You could have some modified gravity or whatever. So I've plotted in this plot an example of just a very simple, where you just take the dark matter and the dark energy as actually being just one thing. So this could be, for example, a model of an interaction between dark energy and dark matter. And we're just modeling the whole thing together as one fluid. And if you do that, of course, because you've got lots of dark matter, then you plot the equation of state as a function of redshift, you end up with this blue line here. So at high redshift, it just looks like matter as usual. And then at low redshift, once the effect of the deviation becomes apparent. So this is just mimicking the DESI Bez-Des-Fit kind of model here, which in itself, if you take W naught WA seriously, gives you a W naught W that goes very negative and violates the null energy condition. In terms of the total with the dark matter, it's not violating anything at all. So this is perfectly consistent with the null energy condition. And it turns out this kind of model is actually really hard to tell at the linear perturbation theory level apart from the other models. And the perturbations can, so what I've done, what we plotted in this plot, this paper with Raphael Koo, who's a postdoc here, he's written down this dark energy model, and that exactly reproduces CPL at the background level because you can just choose your model to exactly fit the background. So all the background things fit exactly if you choose this unified fluid model. The freedom is then in what happens to the perturbations that might be different. So in simple quintessence models, you'd expect the sound speed of the quintessence part to be 1 probably. But if you choose, say, something radically different, where you've got this combined fluid, the dark matter and the dark energy, and the combined fluid has a sound speed of 0, it turns out it's very hard to distinguish. You end up with predictions that are really very similar. So on the left here, I've shown the microwave background spectra and how they differ. And on small scales, you get small wiggles, but they're very small due to changes in the lensing spectrum. On large scales, you would get a little bit of something from the ISW, but this is really not distinguishable with current data and only marginally distinguishable in the future. If you look at what happens to the lensing, there is an effect, but it's still only a few percent on relatively large scales. So it's going to be quite difficult to distinguish from things like changes in other parameters that might be degenerate with it. So the reason why this effect is so small is basically because in matter domination, a lot of the growth happens in matter domination before the dark energy becomes important. And a lot of the effect of the dark energy is at the background level. So the effect of the perturbations is actually relatively minor coming from the low redshift effect. Where you do start to pick it up is if you look at things like galaxy density cross correlations and galaxy lensing. So these two bottom plots here show sort of what you might get at different redshifts with Euclid-like error bars. So the galaxy lensing is not very good, but if you look at this one here for the galaxies themselves, then you can end up with shifts of a few percent at some redshifts. And then the challenge then is whether you can distinguish this kind of model from changes in the bias and other things that you don't know. So maybe you could actually distinguish these models in the future at reasonable significance, but it's not going to be very easy because the predictions seem to be remarkably similar. So that's about it. All I wanted to say, really. So if you take the null energy condition seriously on an individual fluid basis, so in other words, you're imposing that the energy density of the dark energy can't increase with time, then that makes these very strong constraints on how the BAO observables can change with time. That allows you to then map observations of the BAO into sort of what allowed physical models there are. What you find is that the tensions that you see in the data from DESI are actually mostly in directions that are inconsistent with this null energy condition. So it looks pretty weird. It's pulling you into this sort of phantom regime independently of what the actual modeling of that actually is. On the other hand, the fit to ΛCDM doesn't really look bad, especially if you're prepared to buy a sort of shift in the Planck values of the parameters by 1 to 2 sigma. Supernovae are pulling things away from ΛCDM, but it varies a bit between the different things, and things are changing around a little bit. And again, it's in a direction that's not consistent with a null energy condition. And even if you want to introduce this dark energy, it doesn't really help you with the Hubble tension. So there's still a big unresolved problem there. And then finally, there are, of course, other interpretations that's not this separate fluid, which we can hopefully be able to test in the future. If any of these tensions hold up in the future, then it'd be very interesting to test what is actually going on there. And maybe you can do that from the way that the perturbations evolve at lower redshift by being very careful with the low redshift data modeling. Okay, thanks for listening.
Thank you so much. Thank you so much for a great talk. Do you have any questions? Julian?
Yes, thank you, Antony, for the beautiful talk. So you talked about this unified dark fluid model. It's really interesting, but it's purely phenomenological, right? And it has W different from the sound speed, for instance. So I'm wondering if you have some idea of an underlying model that could go in this direction, or if we should look at this as a purely phenomenological model.
I think you can think about it as a purely phenomenological model. I think there are some models that actually do produce something that very much like this, K-essence of some variety. I haven't looked into exactly how these models and things work themselves. I agree, it's definitely not in itself a very natural model either. Yeah, because you've got this funny sound speed and yeah. Yeah, it's only going to be interesting, but what the underlying physics is, yes, I don't know.
Yeah, thank you.
Thank you. Jens?
Yeah, thanks a lot for this really nice talk. What happens if you change recombination?
Well, you should answer that, Jens, I think. So I mean, you'll shift everything in the usual kind of way, right? I'm explicitly here assuming we know the early universe. There's a whole different story about early dark energy changing recombination. Yeah.
Okay,
Which
maybe
you're the
let me
expert on.
rephrase.
I'm sure you
Let
can
me
give that talk.
rephrase it. Do you think that recombination could play an important role in this discussion?
I mean, I guess you're the person who's had the most recent paper on this, and whether that's actually going to help with things. I suspect it's not going to help. I haven't really thought about it, to be honest. I mean, obviously that can help with the Hubble tension side of things by shifting the sound horizon scale. How it helps with the dark energy. The thing is, you're just going to be shifting RS and RD the same way, aren't you? In the more or less. Yeah, I'm not going to make a concrete statement about that. Sorry.
Okay, thank you. Daniele?
Hello, thanks, very nice talk. And I would like to make a comment that in the early stage of my research career, I exactly worked and used like a essence model to unify dark matter model. And indeed, if you do this type of prescription of the perturbation of the pressure, the behavior of the pressure, you are able to interpret the fake dark energy go to -1. But in reality, I'm preserving a null energy condition. And exactly for the same direction that Antony pointed out in this talk. And let me say also that the speed of sound I can produce very small.
This was a K-essence model, was it?
Exactly.
Yeah. Thanks.
Thank you. Nico?
Yeah, hi. Thanks for a nice talk. I was wondering, so can you explain the UDF? Is it just like some sort of version or privatization of the CPL?
So this just means UDF stands for Unified Dark Fluid. So it's just taking one fluid model. So I mean, in terms of what you get for your linear cosmological predictions, if it's dark, it only interacts via gravity. So you're free to just combine the two, as many dark things as you like into one fluid. And then you basically just got one one, the sound speed, an equation
And
of
then in
state.
some limit you can obtain.
So here
separate,
this is just matching the evolution of that thing
right.
to reproduce the effect of the CPL plus dark matter.
But
Then you're
has
free
there
to
been
choose
any
the sound speed.
has there been any work on moving away from CPL and doing something, because it's not, I mean, you mentioned it's not the best parameterization anyway.
I mean, there are loads of other ways of parameterizing and people have done these sort of binned reconstructions of
Yeah,
evolution
exactly.
and things, yeah.
But should we be doing our analysis in terms of different parameterizations, or just stick with CPL? Because I mean, we're just redoing the same thing over and over.
Well, I suspect the train has left the station with CPL, hasn't it? I mean, everyone's always going to plot CPL because that's what everyone does. So I think as long as you're very careful about interpreting what exactly it's telling you, it's clearly a useful null test of lambda CDM in a sense that's telling you something that's deviating. It's a bit trickier to interpret different points in the space, as I talked about. I don't immediately know any other parameterization that's obviously better on all dimensions, put it that way. Yeah.
Thank you. Anjan?
Yeah. Hi, Anthony. Yeah, it's a very nice talk. I just want to mention that there's a recent paper by Eric Linder and Robert Caldwell, where they were talking about that this null energy condition is basically this R mu, V mu, V mu. It actually acts on the total energy momentum tensor in that sense. And in that way, there is no violation of the null energy condition that is there. And they have actually given some example where that you can write two dark energy model or two fluids actually apart from the matter, and that can actually mimic a model like CPL that is violating the null energy condition in a sense, like the for the dark energy. So if you can comment on that, if you have.
Yeah, that's right. So that's basically what this UDF model here is. You could take an interacting model as being some effective single fluid, and then you find that this equation of state is indeed perfectly consistent with the null energy condition. So when I defined what I meant by null energy condition, I said I'm interpreting it as meaning the constraint on the individual fluid, not the total. So it's really a constraint on the non-phantomness of it. If you write down the null energy condition as people have used it for these sort of theorems about singularity formation and things, it is true that it's normally defined in terms of the total energy densities. But I think there have also been quite a lot of papers now using it applied to individual fluids as well. But it clearly is still linked to various physical things. For example, if you're trying to get a scalar field model, it's very difficult without doing funny things to kinetic terms to get something that violates the null energy condition applied just to that fluid.
Okay, thank you very much. Thank you.
See, there is a question in the chat by Manoj.
If we're trying to solve the Hubble tension by introducing dark energy, you've got this constraint that you can't do that basically, because if you put in null energy consistent dark energy, then you only get this Hubble value being lower than in lambda CDM. So this is coming from the fact that your theta star, the angular scale of the acoustic peak seen in the microwave background, is fixed. And if you put this condition, then everything is monotonic. So the value of the density of the dark energy today has to be lower than lambda CDM. So if you want to get a higher Hubble parameter, you've got to violate this, and therefore it's violating the null energy condition.
If we can thank Antony again. Thanks a lot for a very nice talk.
Thanks, bye.